Okay, we're at lecture number 8. The last lecture we started talking about general relativity was the introduction of the equivalence principle. And in particular, we noticed the strong equivalence principle can lead to gravitational redshift. It means a light, when propagate parallel or anti-parallel to the gravitational field, will be shifted to red or blue, depends on whether going against the gravity or in the same direction of gravity. And in this lecture, we'll continue to section 4.3. We'll talk about gravitational time dilation. The clock will run a different rate at different gravitational field points. And talking about GPS, its operation actually really depends. That we need to make the correction correspond to relativistic time dilations. Okay. So we talked about gravitational redshift, which is redshift of the light emitted and received when the emitter and receiver are stationary. They're not moving, not like Topla's case. Okay. And then we'll wonder, how can we receive a different number of peaks that's different from the number that's emitted? Where did the extra peak go, or where did the missing peak go to? Einstein gave a simple answer. We're talking about frequency. Frequency is number of peaks per unit time. So therefore, clock at different gravitational potential points can have different frequencies because the time rate may be different. In which there's a gravitational time dilation. Clock run at different rates at different gravitational potential points. So here's the formula for gravitational redshift. Frequency shift related to the potential difference. But now the frequency is directly proportional to one of the inverse time rate, proper time rate. So therefore, this left-hand side can be written as omega 1 is 1 over d tau 1, omega 2 1 over d tau 2, so on and so forth. And if we multiply the product of d tau 1 times d tau 2 on the numerator and denominator, and the first thing becomes d tau 2 minus d tau 1 over d tau 1. Okay, so this is a time dilation effect here, which is related to the potential difference. So time dilation is related to the potential difference. From going from here, I interchange the tau 1, tau 2, so I pick a minus sign, cancel minus sign over there. So therefore, a clock at the higher potential, in which if say phi 1 is greater than phi 2, if this is positive, then the left hand side must also be positive. So therefore, d tau 1 must be greater than d tau 2. So the tau 1 part, the higher potential part, run at the faster rate. The time interval is bigger. By the way, you wonder if I put here divided by d tau 1, I could have done put d tau 2. It's just different by high order. We're only working with the leading order. Okay. Now, this way deriving the gravitational time dilation, in some sense we use a standard procedure involving light signals. But it's kind of complicated because we need to remember taking into a Doppler effect and then cancel by the gravitational redshift, and then we have to convert it into time intervals. Okay, so we have the result, but the derivation seems complicated. We wonder whether there be a more direct derivation. Yes, we'll present the next direct derivation. In fact, it's also nice. It's related to the time dilation of special relativity. Okay, so we're going to derive the time dilation more directly, and the the trick is that we're going to use 3 identically construct clock 1, clock 2, clock 3. Clock 1 and 2 are stationary at, one is located at gravitational potential phi 1, the other one is located at gravitational potential phi 2. Okay, and then the third clock, we're just going to drop it so it's in free fall, passing phi 1 at passing clock 1 at phi 1 and passing clock 2 at phi 2. And of course, when it's passing with different speed here at u1 and u2. Or another way, in the rest frame of the clock 3, you will see phi 1 going up with u1 and clock 2 going up with velocity u2. And then we can relate the clock of the measure, the third clock, clock 3, with the clock measure uh, 1 and clock 2. And because it's time dilation, we don't have to worry about, because when it compares clock 1 and clock 3 at this point, they are both at the same gravitational potential point. So therefore, there's no gravitational time dilation. In fact, we just use special relativity because they are in relative motion. Okay. So this way we can relate time clock 1 and clock 2 to clock 3 in this way. But they are related in terms of the velocity u1, u2. The difference u1, u2 can then be related to the gravitational potential of these 2 points, because this clock is falling. The reason it's moving because it's falling through these 2 positions. And so these 2 quantities can be related by energy conservation. So therefore, I can relate the difference in time to the potential difference, and we're getting the gravitational time dilation. And we'll leave that an exercise as a break exercise for you to do. I will outline the procedure again, and I want to ask you to derive, using this setup, to derive the gravitational time dilation. Okay, that's all for this. It's a short